And so I would like to announce Mr. Oliver Schauerte from Volkswagen. He's the head of materials research and vehicle projects. And the title of his presentation is Lightweight Solutions for E-Mobility, Circular Economy and Carbon Footprint. And I'm really curious what you're going to present to us. And the stage is yours. Thank you so much.
Yeah, thank you, Mrs. Brickweder. Thank you very much for this kind introduction, and also from me, a good morning to everybody. Great to see that you all came here that early in the morning to the Hanover Fair. And yes, I'm very happy to be here with just 2 years delay, but at the end, I'm really happy and really great to interact with people in reality again, also with people who don't have a big mask in their face. So let's talk today about lightweight solutions for e-mobility, for circular economy, and for carbon footprint. And even in the last 2 years, a little bit, the things had changed, so I had really to rework my presentation. It's not really necessary to present about Volkswagen Group here in Hanover, but just keep in mind, I'm representing the group innovation, the former group research of Volkswagen, and the group research, as the name group indicates, is working for all the brands. So all the brands you see here are paying for us according to their annual turnover and supporting our work. Also, this is just for showing off. However, if you talk about introducing new material, introducing lightweight solutions, we have really to keep one number in mind. This is more than 40,000 vehicles that we produce worldwide a day. So this is always the dimension that you have to keep in mind if you simply say, oh, just change the structure, not the problem. Just take magnesium, not a problem. It is sometimes a problem. And then why we are thinking that Volkswagen has to go to zero, why Volkswagen Group has really the goal to make its contribution, a big contribution to the carbon reduction in the world. So from the greenhouse emissions, 14% are caused by the transportation sector, and simply according to the size of the fleet of the Volkswagen products, Volkswagen alone is contributing 1% of the worldwide gashouse emissions. So we think as a company that we have to deal with that and we have to do something. Now let's come to the technical questions. First about the future mobility changes. So what are the customer expectations and what does it mean for us, for you as engineers, for the needs we are confronted with and with the work we have to do? Sure, customers expect for the more distant future that they have autonomous opportunities by using their cars. That if they use this more or less autonomous, you see I'm a little bit careful, autonomous opportunities, they want to be more private, they want to be more convenient, they have other expectations to the interior of the car and to the use of the car. They want to use the gained time to be productive or efficient or to play computer games. They expect much more that their mobility and the mobility they choose is sustainable. Still, most of the customers expect that they will still have an option to drive their car manually. Especially in the last 2 years, according with the pandemic, people expect much more about hygienic issues and about well-being in the cars. Sure, they want to be seamlessly connected with their cars, and sure, they want to take into account that their car takes into account everything that's going on in the actual traffic situation. Now I try to face these or to transfer these customer expectations in our work. And so for engineering and especially for material solutions, which are always very, very closely linked to lightweight solutions, we have really to deal with completely new fields of action. So if you just think 10 years ago, lightweight design was, okay, I make a smart construction and then I replace the steel by aluminum, or the aluminum by magnesium, or in the best case, with carbon fibers. And today, we have really new processes like 3D printing, like the elementary bonding, so bonding without using additional spot weldings or clinchings. We have friction stir welding processes, spot friction stir weldings. We have new fields of applications. Today, I will later talk a bit about We have also to think if a lightweight approach is probably more to deal with new battery materials, with new semiconductors, new e-machines. We have sure new materials to think about, because today we take into account the carbon footprint of our components and of the materials, something that was just 6 years ago, 8 years ago, not really something that was discussed. So we have suddenly to think about biointeriors, about wood, about recyclates, about rare earth materials, so also the availability. So when we come to the from lower right, it's also the new demands. It's about carbon footprint. So we really have to report for every single component in our car, not only the weight, but also the carbon footprint for the materials used for it, the carbon footprint for the production of the component, and for the assembly process that we have in our factory. So this completely shifts the point of view for a number of materials and lightweight applications. And sure, customer expectations are changing. They are asking for virgin materials. And sure, also the availability for the materials, because suddenly with the e-mobility, we have a growing use for a number of metals we never thought about before, like cobalt, like lithium, and suddenly the question is asked, how long time this will be available. And then finally, if we develop new materials, we have to talk about new methods. We have tools that were not available just 6, 7, 8 years ago, like quantum simulation, like bioprocesses, like high throughput simulations, and so on and so on. So now, I think just a few years ago, I always showed this spiral the other way around, but in the last years with the e-mobility, this has really changed. So if we come from an e-mobile today, we are suddenly faced with the problem that we have a very, very heavy battery. We will also, according to the changed customer expectations, we are faced with more electronic components. We need more powerful e-drives to move all this. Sure, in the next aspect, we need a reinforced body in white, also according to the new regulations on crash and safety. And sure, this heavier weight will need a reinforced chassis, and so on and so on. Now, today, very often people say, okay, but I have recuperation, so I do not really have to care for the weight. But we see now, it's my impression, that we see now if you just for 1-2 years, you lose the discipline on lightweight engineering, suddenly the weight is exploding. And if you look on all the cars we have on the market there, and you compare it, if possible, to comparable classical combustion engine vehicles, you really see a gap of 200, 300, 400, 500 kilogram. And this causes also other aspects. So the crash masses are higher, again contributing to the weight spiral. You have significant tire wear in some of the vehicles, the brake wear, and sure, the range is not really that much infected, but it has an influence, and we are really fighting for every mile. And what people often forget is if you have a car that is 300 kilogram heavier, it's 300 kilogram more car that you have to pay for. It has to be produced and it has to be purchased. The payloads are going down, and sure, in the luxury segment and in the heavy-duty segment, we're coming into a situation where we really have to discuss about the validity of the driving license. So we have to really face the fact that lightweight design remains a company goal. So if we now come to this point, I have now created this triangle to just visualize a little bit the situation, how there are also other theories, but generally you can do lightweight. If you start here in the lower left, you can achieve lightweight through constructive solutions. That is always the smartest thing. A smart construction doesn't cost you very much. You can have a lightweight orientated vehicle concept. You can have a load path orientated design. You can, and even in the direction of the e-cars, you have more options on this. That can you take into account. The most expensive solutions is very often the lightweight through materials. You simply take your steel and replace it by more expensive aluminum or more expensive magnesium or even more expensive carbon fiber reinforced plastics. But also here new solutions and new players are coming to the market. Not only wood or biopolymers, but also I think a lot of chances are hidden in the press hardening steels, for example. And then something, I've called it conceptual solutions. I'm still working for the right expression. The idea, if I spend money on lightweight design, one of the smartest ideas in e-mobility for lightweight design is if you spend the money not in a new alloy, but in a more efficient battery. If you have more efficient batteries, you need less batteries. That's the easiest way to reduce your costs and the weight. Same for more powerful magnets in your for high efficient e-machines and so forth and so on. I mentioned before that we have to take into account today the carbon footprint. So we can not only watch on this and think what would be the best solution. We really have to add a third dimension, and this means the carbon footprint or the carbon advantage we achieve by using a certain material. And if we lay down the triangle that I've shown, and we go on the next axis, then we see that it's just a very rough estimation. But then we see that, for example, the choice of magnesium and carbon fiber reinforced plastics has a big lightweight impact, but unfortunately not really a good impact on the carbon footprint. While wood is not really a lightweight material, it is light, but not the lightest solution, but it would even be higher because it even gives you a carbon benefit, not only a carbon footprint to the car. Same as for the batteries. If you need less batteries, you have a better carbon footprint, very, very simple. But if you need work with more powerful magnets, you have maybe to introduce more rare earth metals, more complicated energy-intensive processes, so probably your carbon footprint will be not as good. But again, this is just a very general presentation. Now, we talked about carbon footprint and we talked about lightweight, but you also have to talk about circular economy. In the past, now our approach was normally that we use something in a linear economy, we use something and at the end we put it to the waste. Today we are mainly focused, confronted with a recycling economy, so we use something, then we reuse it, maybe we downcycle it, so we use it first in the car and then, I don't know, somewhere in a toy or in a plastic waste paper basket or whatever. And the idea must be a circular economy where we really use always the same materials. And for this, we have created for ourselves around the inside the biosphere, so we have the technospheres. So what is when we make a car, we need a factory, we get material supply, we make components from it, we assemble the product, then we send the product to the customer uses it, and then, in the best case, after the use time, for each step in the production, we find a solution. So probably if we refurbish the complete car, bring it back to the market, probably we dismantle it and use single components, or for those parts we can't use anymore, that we can't refurbish, we still have the option to win back the material and to recycle it. This is the idea. The same, so the lower strokes there is about the energy and the resources use of the factory itself. So this is now the next step we have to keep in mind. Now I come to a number of examples how we deal with this, with these interactions to give you a feeling about how we are dealing with it concretely and how we are really working on these questions. Because at the end of the day, you will not have you can make general strategies, you can make big pictures and big PowerPoint presentations, but at the end of the day, you have really to deal with very, very concrete questions, and this is where I will now focus on with giving you some examples. For example, the ID4, we see a number of the ID4 is using mainly in the plastics. It's about 350 to, depending on the version, 350 to 380 kilogram of plastics used in the car. Most of it is thermoplastics, but also elastomers and duoplastic materials. And the recycling contents, as you see there, is still on a disappointing level. So we really have to deal with it. And I like very much this presentation, although it's 3 years old. But it simply shows the use of, or the production, the worldwide production of plastics, and over the time. And we see that this curve is not stopping. So the material that is available for recycling, that is coming to the market, is becoming more and more and more. And if we talk about recycling market today, you have maybe to think about 10 years old project. So if you look on the curve, you see we talk about the amount from 2010. But if you think about the cars we make today, or that we make the concepts today, we have to talk about the amount that is then coming on the market, which is from 2020, which is nearly twice as much. And this means today, if you take the numbers from 2018, the ratio is more or less the same. Most of these plastics are manufactured from fossil bases, but we really have to go down to zero to achieve the goals on carbon footprint. This forces us an enormous amount of capacities, not only the automotive industry, but also the consumer industry and in the chemical industries, to recycle as much as possible of it, but also to find solution to improve plastics by bio additives, by bio-based material that you add to the material. And sure, we are also working on the questions how you can reuse carbon dioxide. I know it's from an energetic point of view, maybe the holy grail of the most complicated question, but if you really come to the time where we have green energy really available as it is promised by the politicians, then you can use the green energy to really reuse carbon dioxide and make plastics from it again. Now, materials, for example, another completely different field is the biomaterials. Why having a carbon footprint at all? Why do we need that? Why don't we think about solutions where we don't have a carbon footprint? So, for example, interior parts like seat covers, like roof liners, like door liners, and so on and so on. We could make it from hemp, from grown structures, from agricultural byproducts. We could really create materials, I will show later, from the reactor, which are from a bioreactor, which are completely in their production, more or less completely carbon-free. And the other option is to make parts from wood. There's no really use of wood in automotive industry, but why don't we think about using it? What you see in the news is maybe a little bit confusing, but it is really, we have so much knowledge about fiber industry, about fiber manufacturing, and we have so much wood. Especially beech veneer, buche. Beech material has the highest ratio from strength to density, and we have so much beeches only in Germany, and then we have not talked about Austria and Poland and Czech Republic. We have so much, we make charcoal from it for barbecue because we don't know what to make with it. So this is the simple truth. And what you see here is a component that we have developed on an example. It's a door impact beam, a steel door impact beam that is replaced by a wood solution in a weight-neutral way, and then additionally also the bitumen mats that are normally glued to the door inner, then are introduced into this wooden structure. This just as an example for wood. Now biomaterials, we have now classified them. So we classify on the one side, we classify bio-based products as agricultural byproducts. Best example is material, it's not from us, it's on the market, like the pineapple textiles. They use the leaves of the pineapples to create the fibers and to make something from it. It's a good product because there's nothing else you can make with it. Then we talk about artificial leathers. I will have an example afterwards. And then sure, we have the bio-based process, growing structures where you can maybe create really leather-like materials just from yeast or from mycelium, from Pilzen, from mycelium, or maybe even wooden byproducts from wood industry that could be compressed to components. What we will never do is using any agricultural ground that is dedicated to food production. We will never use this ground to create anything for our cars. So no agricultural ground and no food for cars. It must be always the byproducts or created in bioreactors. So this is, for example, the example for the leather. Leather is a natural product. It's very, very robust, very, very sustainable in this case. But people often forget it has not really a very good carbon footprint. Because before somebody shooting me, there are thousands of calculations about the carbon footprint of leather, because it's very, very difficult to assess which share is now for the meat and which is for the skin. Nevertheless, it is significantly high, and unfortunately higher even if the cows are living free on the ground and are not somewhere housed, because then all the gases are going outside. Artificial leather is quite good in its impact, but could be improved, and sure, customers are hesitating, saying, okay, I want to have a vegan solution, but plastic, I don't know. But now we have really found a solution to improve these leathers by filling it with byproducts. We have an example that you find even in the press. We call it the coffee leather, where we have the project with Heims Coffee in Braunschweig, where they provide the silver skins of the coffee beans. There's nothing you can do with it. You can just burn it. And so we mill it, and then we fill it, feed it into the plastics, into the polymers that we are using for the artificial leather, for the leatherette. And so in the end, together with the hemp bag, we can really create a leather with a bio content of more than 50%. And that's a nice first step. More projects to come. My favorite is the beer leather. We are working on that. You have also that similar byproducts. Another idea, for example, we have already dealt with is the paper composite. You can compress paper very, very intensively, or you can really create a leather kind of a liquid, so that the tears that it really falls apart, and then you can afterwards infuse it with thermoplastics. Yes, with thermoplastics or with duroplastics, those thermosets, and then compress it. But you can compress it either to exterior parts, as Porsche has tried and demonstrated, or to draw in a paper composite from a carbon footprint. Is interesting. It's not really lightweight, but it's not really heavy. And you have it everywhere in the world. Everywhere in the world, people collect old paper. So you have very, very short distances for the production, for the collecting, and so you have the good carbon footprint on this side. So very, very interesting project. Another thing is, I have to hurry a little bit, steels. I think it's important, especially at the Hannover Fair, to talk about steel. Steel is still the most important material. 96% of the worldwide used automotive body in white materials is simply steel. We have a large variety of steels that we are using in actual cars, and we think that we have, with press hardening steels, we can reduce the number of steels that we use and therefore change the properties just in the press hardening process by different heat treatments and forming processes and forming temperatures, so that we can use the same steel for different applications depending on if you need a tensile strength of 2000 MPa or maybe just of 1200 MPa, but it's always the same chemistry, so it can always come from the same metallurgical process. Then let's talk about magnets, for example. This is now just to keep in mind. If we can really improve the permeability and reduce the losses, and can really reduce corrosivity and improve polarization, we have better soft magnetic materials, on the other hand, we have the mechanical properties. What we would like to achieve, sure, is soft magnetic alloys. It's normally iron, silicon, something, steels, electrosheets, so that we can really go to higher revolutions, or to a better compressed material, to a more compact electrical engines. In the best case, combined, sure, with better hard magnetic materials. Just as an example, as a reminder, same here again. It's not only the alloy development, as you see here, iron, silicon, and something. It's also about the design. It's also about using the optimized magnetic fields. But I don't want to spend here too much time to use the last 2 minutes. I'm given is a little bit about new methods. So finally, we can improve all these things. If it's a lightweight design, if it's a physical material, if it's a battery material, we can really achieve improvements today by using new methods. And these are the methods. What I'm talking about is really the quantum simulation. It's the high throughput today. So very often you read, when you talk about new quantum computers, it's always a question, where the hell I need that much power, that much computer powers? There are always two examples. It's traffic simulation and it's material development, so that you can really combine different metals. In the past, it was very much try and error. Oh, I take 2% more silicon and maybe a little bit less titanium and a little bit more molybdenum, then it should work. Today, we really run through all the project, through all the elements on the computer, and so we can really really precisely predict the material by simulating the interactions of the electron with the nuclei and with the neighbor atoms or the neighbor nuclei. And this really allows you with quantum simulation to predict very, very precisely all physical components. Not the mechanical properties, but the physical properties, and this helps very much. And so we run today, not in a closed loop, but finally we run through all the projects, through all the components, from electrons about atomic structure, and so on. And we have tried to put this also in a kind of a categorization. So this means we make materials engineering, we make materials exploration, and we make materials evaluation. And engineering means really that we have numerical ideas for the modeling of the, for the simulation of the materials. Then we can replace this materials exploration. We really run through the periodic table of elements. We replace the experimental screening by computer technologies, and then the materials evaluation. This means that we really make a materials hypothesis, and we replace the experiments by verifying materials hypothesis in conceptually correct results. So it's numerically, categorically, and conceptually. And in this combination with this is something we are really doing in our team very, very successfully, also with universities in the United States and in Germany. And this maybe finally should give you a little bit an outlook in the future, how materials design will happen in future, and how this could, I think, from looking back into this presentation a little bit, how this could really contribute to lightweight design and to carbon neutral, hopefully one day, carbon neutral mobility. So finally, if you have the conclusion, we have to face the fact regarding what is the discussion, is lightweight, LightCon. The weight spiral has turned around, and the higher vehicle masses cause more crash masses, cause more cost, cause more wear. We have new demands for footprint, for carbon footprint, and for the components and for the production processes as well. The carbon footprint will push solutions away from the classical lightweight solutions. And however, modern materials development will be part of the solutions every day. So I can invite everybody to really go to the university and learn a little bit more about material sciences, because lightweight design remains one of the main challenges. So thank you very much for the presentation, for listening.
Thank you so much, Dr. Schauerte. So I have learned a lot. So the next task will be veggie. And coffee, beans, beer, whatever can be used. So I'm absolutely sure that you have a lot of questions. So please take one of the microphones, because this session will not be streamed but recorded, so that our people who want to see that can follow your questions. Are there any questions in the room? Perfect. Would you like to take the microphone, please? Yeah, it's right next to you.
Good morning. Many thanks for this very interesting presentation, Mr. Schauerte. Regarding this artificial leather, what are the costs compared to the natural leather today, and what do you expect will be the evolution of the cost for such artificial materials?
It's a question if you talk about cost per kilo or per square meters. But let's say and it's very much depending on the quality of the natural leather that you're using. But there's a factor in costs of at least 3, 4, 5, 6 in this range. So, and artificial leather is, I don't know, €5, €6, €3.
So the cost would be also a big driver in the future for the new materials we need, to reduce the cost of these new materials we need, no?
Sorry?
The cost of the new materials will be a driver.
It will be more or less on the same price range of the as the normal artificial leather. The good thing is that we may be a little bit cheaper. It's more or less in the same range, simply because what you are using as a filling material is simply waste from whatever process. In this case, it was coffee production. There are a number of other options, but what you're using is more or less waste. So you only have the transportation costs. It's a little bit more cost in the process, but a little bit less cost in the raw material.
Are there any more questions? Obviously not. So you've answered everything in your presentation.
Yeah.
Big thank
Good
you,
idea.
Mr. Schauerte. And yeah, I guess you will be here with us for a couple of moments.
I can later have a chat, no problem, and coffee.
Perfect. Thank you so much.
So, thank you very much. Bye.